Okay, so we were discussing this shell energy balance. So in last four problem, I think four couple of problems we have discussed actually, just electrical heat generation, and couple of problem we have discussed nuclear heat generation, where we were concentrating on a problem where only there was a molecular transport. The energy was transported by using conduction only. That was the case in previous 3-4 problem what we have discussed in shell energy balance. Now, today we will see how to handle when there is a convection. There is a convection, and this is the term which is associated with convection. So even though it is, so initially also I told that this molecular transport and this molecular transport has a different meaning. This is the work done on a system by molecular transport means because of molecular motion. This is energy work done, or this is work done on the system. This is done work done on by the system because of the molecular motion. And this molecular transport means on molecular level. And molecular level because in absence of bulk motion. Okay. So whenever there will be a convective transport, this will be associated with convective transport, which this term work done by a system or on a system by molecular transport is associated with convective transport. So today we'll see how to handle the problem when there is a molecular transport as well as convective transport. Both are there. Molecular transport is also there, convective transport is also there. As soon as convective transport is there, so it will be associated with the work done on a system by molecular transport. So this, whenever these three, so as soon as convective come, this will come. So three will come together. This will generally term as a combined energy flux. So combined energy flux will be a conductive flux, convective flux, plus work associated with the molecular transport. So this already we had a brief discussion about this convective flux, and we will discuss in detail today. So this convective transport. So convective transport will be always associated with the velocity, bulk motion, and then it will be energy per unit volume, So that we can represent in detail, taking the help of thermodynamics and all other kinetic energy fundamentals. So consider a three mutually perpendicular element of area ds at point P. So convective transport is always associated with the velocity. This we know that. Convective transport means bulk motion, and bulk motion is characterized by the velocity. So consider a three mutually perpendicular element of area ds at point P. So these are the three mutually perpendicular. This is the perpendicular area to x direction, this is the perpendicular area to y direction, and this is the perpendicular area to z direction. All three perpendicular areas are at point P, and these three perpendicular areas are perpendicular to each other because these three axes are perpendicular to each other. So this is a perpendicular area to x-axis, this is the perpendicular area to y-axis, and this is the perpendicular area to z-axis. Okay, and as I am telling that convective transport is associated with a bulk motion. Bulk motion is characterized by velocity. So consider a velocity. So this is velocity v, velocity v, velocity v. So vx is a perpendicular or x component of velocity v. Vy will be the y component of velocity v, and vz will be the z component of velocity v. So, so we are combining everything actually, x component, y component, z component, and convective transport in all the direction. So if dx, say if v is a velocity of the fluid, so the volumetric rate, okay, volumetric flow rate of a flow across the surface element ds perpendicular. So the volumetric flow rate perpendicular to ds. What will be the volumetric flow rate? So if v is a velocity, what will be volumetric flow rate in to x direction? That will be a vx into ds. Okay, vx into dx. This will be the volumetric flow rate. This will be meter per second, and this will be meter square, and this will be meter cube per second. So this will be so dv. V into dV. So this you might have been used so many times. This will be a volumetric flow rate in x direction. If V is the velocity of the fluid, Vx is the x component of the velocity, and ds is a perpendicular area to x-axis. So Vx into ds will be the volumetric flow rate of the fluid, or volume flow of the volume rate of flow across the surface at element ds. Okay, this will be a volumetric flow rate. This will be the rate at which energy is being swept across the surface element in x direction. This we are discussing about only x direction. If this is the volumetric flow rate, so if I have energy per unit volume, if I have total energy per unit volume, that will give me a rate at which energy is being swept. So here we will consider this is the total energy. So this is total energy per unit volume. This will be kinetic energy and this will be internal energy. This is total. This is a kinetic energy per unit volume and this is the internal energy per unit volume. So this will be a total energy per unit volume multiplied by volume. This will be a rate at which energy is being swept across the surface. Okay. So this will be a half rho into V square will be the kinetic energy per unit volume. So because convection is associated with a bulk motion and bulk motion is characterized by velocity and energy associated with the velocity is the kinetic energy. So kinetic energy will be there whenever there will be the convection and the internal energy. So rho into V is the internal energy per unit volume. So internal energy per unit volume, and this will be the volumetric flow rate. So what will be this? So this will be this is in x direction, rate at which energy is being swept. Because this is characterized by velocity, so this will be a convective energy flux. This will be convective energy rate at which energy is flowing by convection in x direction. Rate of energy flow in x direction because of convection. Convective rate of energy flowing in x direction. So this will be a kinetic energy, this will be an internal energy, this will be a volumetric flow rate, and this will be x component velocity, and this is the perpendicular surface area in x direction. So this is clear to everybody? Anybody has any doubt? This is actually total energy per unit volume. This is total energy per unit volume. So if you go in thermodynamics details, so previously we have discussed this total energy in terms of specific heat at constant pressure, actually Cp rho into Cp into T, that we have discussed, that is also. So if you go in detail, so this internal energy is associated with the Cp actually. So you need to, I think you need to associate that first and second law of thermodynamics. There you can get the relation between internal energy and specific heat at constant pressure. And this was neglected that time. This was neglected, but now here we will consider this also, because half rho V square is the kinetic energy per unit volume, and this will be smaller. If velocity is very small, this will be smaller, and this will be internal energy per unit volume. This is also energy per unit volume. This is kinetic energy. If you go in details of this term, half rho into V square is a kinetic energy per unit volume. This is kinetic energy per unit volume. This is internal energy per unit volume. This two is a total energy per unit volume multiplied by volumetric flow rate. It will give me a rate of energy flowing in x direction. This is the convective energy flux in x direction. So this is convective energy flux in x direction. Similarly, this will be a rate of convective flux, not flux, rate of energy flowing in y direction because of convection. This is rate of energy flowing in y direction because of convection. This is the rate of energy flowing in z direction because of convection. So rate, how to get a flux from rate? Divided by area. So I can divide the area. So this is the rate of energy flowing in z direction because of convection. So how to get the flux? Divided by area. So half, this will be energy per unit volume multiplied by velocity. It will be convective energy flux in x direction. This will be convective energy flux in y direction, and this will be convective energy flux in z direction. So rate and flux, how to get a flux from rate? So divided by area. How to get a Flux from rate multiplied by area. If rate is given and I need to estimate the flux, then it will be multiplied by area. If rate is given and I need to get the flux, then divided by area. Okay. So this will be a energy per unit volume, total energy per unit volume. Initially we had neglected this in previous discussion. Now we have added this kinetic energy per unit volume also. This is energy per unit volume multiplied by velocity in x direction, x component of velocity. This is energy per unit volume multiplied by y component of velocity. This is energy per unit volume multiplied by z component of velocity. So now if I combine this, okay, using direct delta function, sometimes you don't have x velocity, sometimes you don't have y velocity, sometimes you don't have z velocity, or appropriate value of delta x, delta y, delta z can be used. So combinedly, I can write this. This will be energy per unit volume multiplied by velocity will give me a convective energy flux. So this will be the convective energy flux. Okay. So now here after we will be using this convective energy flux, which will have kinetic energy as well as internal energy per unit volume multiplied by velocity. And now as there is a convection, there will be work associated with the motion of the molecule. Motion of molecule means displacement of the molecule. Okay, because there is a convection, the molecules are moving from here and there. Because of this motion of the molecule or displacement of the molecule, there will be work associated with that. How to account for that, that we'll see. Let F is a force. F is a force, and then distance, moment made by molecule is dx. Okay, F is a force acting on a molecule, and dx is a distance moved by the molecule. F into dx will be the work done. Work done will be force into distance or displacement. dw. Okay, so displacement, work is a force into displacement. Now work per unit area, that will be a rate of work done, not per unit area. It is work per unit time, not area. Work per unit time. dt is a time. So this is work done. So this will be a rate of work done. Rate work per unit time. That will be F into dx by dt. What is that? This dx by dt is a velocity. Okay, displacement per unit time is a velocity. So rate of work done will be force into velocity. So rate of work done per unit area. So what will be rate of work done per unit area? So rate of work done per unit area will be a force per unit area into velocity. That will be a shear stress into velocity. So rate of work done per unit area because of molecular moment dx. So rate of work done per unit area because of molecular moment dx will be a shear stress into velocity. So this shear stress into velocity can be interpreted as a rate of work done per unit area whenever there is a convection. Whenever there is a convection, so shear stress multiplied by velocity will be associated with the rate of work done per unit area. Logically, say this is force. Force into displacement is work. Work done per unit time is the rate of work done. Rate of work done per unit area is a shear stress into velocity. Force per unit area, shear stress into velocity can be interpreted as shear stress into velocity. Now we'll go reverse because we have x stress, y stress, z stress. From that we'll get the work associated with the molecular motion. So shear stress, that pi is a shear stress. Okay, shear stress. So shear stress in x direction. X component of shear stress is pi x. That pi is a shear stress, and x component of momentum flux is pi x. Pi x into dx. Okay, shear stress multiplied by surface area, perpendicular surface area, will give me force. Give me force exerted in x direction and rate of work done. Okay, rate of work done. This force multiplied by velocity will be the rate of work done. Force multiplied by velocity is the rate of work done. Rate of work done per unit area. Rate of work done per unit area will be the shear stress into velocity. Shear stress into velocity will be the rate of work done per unit area. This is accounted as a work flux because of molecular motion. Work flux because of the molecular motion, that will be a shear stress into velocity. This is for x component. Similarly, I can have for y component. Similarly, I can have for z component. So z component, and this will be a, this is again pi xx. Pi x will be the x momentum, x shear stress that has a 3 component, because this is the tensor. This will be a x momentum because of x flow in x momentum because of x momentum flowing in x direction. This is y momentum flowing in x direction. This is z momentum flowing in x direction. Similarly for y momentum flux, actually this is y momentum flux. So this will be a work associated with x momentum flux. This is work associated with y momentum flux. This is work associated with z momentum flux. So total work associated with all momentum, this will be a work associated with x momentum, work associated with y momentum, work associated with z momentum. Moreover, this is the shear stress. Okay, this is the total stress. Okay, total shear stress, and it is decomposed in, it can be interpreted into two components. One will be momentum flux because of viscous forces, another will be momentum flux because of pressure forces. Here will not have pressure, here will not have pressure. Similarly, I can have, this will be a work flux associated with x momentum, work flux associated with y momentum, and this is work flux associated with the z momentum. Correct here, actually this is z momentum. So this will be a total work flux. Total work flux using direct delta function. Direct delta function we have used so many times. It will have a unity value in appropriate direction, otherwise it will be 0. This will be a total work flux. It will be a delta x. This will be x momentum, x work flux. This will be delta y work flux, and this will be delta z work flux. Okay, this will be a work flux because of molecular motion, and conductive flux. Conductive flux, you know that Fourier law of heat conduction. So Qx is x conductive flux, y conductive flux, and z conductive flux. So most of that, and now this is all we have discussed now. This will be a convective energy flux. Okay, this will be convective energy flux. This will be a conductive energy flux, and this will be a work flux associated with a molecular transport. Okay, so whenever there is a convection, this will accompany with this convection, and then conduction will be there. So whenever conduction and convection is all together, instead of handling this separately, actually convection, conduction, and this work associated, we will handle combined energy flux. So this combined energy flux will be a, this will be a convection plus work associated with molecular transport plus conduction. Okay, so hereafter, whenever there is a convection, we, instead of using convection, conduction, and work associated with molecular transport, we will be using this combined energy flux. Anybody has any confusion over this combined energy flux? Most importantly, this work flux. Everything is clear for work flux? Yeah, roll number 92. Roll number 92. So can you just briefly explain what is given on a slide? I'm not able to hear you. Roll number 92. Roll number 93. Sai. Roll number 94. Can you explain what is given on slide?
As of so we are transport as of derived energy and then rate of per unit. From there, the combined products.
So hereafter we will be using this combined energy flux. This combined energy flux will have three components. One will be this convective energy flux. Another will be a work flux associated with the molecular transport. This is what work flux associated with the molecular transport, and this will be a conductive energy flux. Okay, this will be conductive flux, convective flux, and this will be work associated with the molecular transport. This already we have discussed how shear stress multiplied by velocity can be interpreted as a work flux. Okay, so instead of this shell energy balance equation, so this convection, this will be conduction, and this will be a work flux associated with the molecular transport multiplied multiplied by area. This will be a rate. So instead of that, we'll be handling this shell energy balance equation. Whenever there is a convection, we'll be using this rate of combined energy flux in. So this is actually combination of all these three. Combination of all these three will be the combined energy flux. So this will be a rate of combined energy flux in, and this will be a rate of combined energy flux going out. That will plus rate of work done on a system by external force plus rate of energy production, that equals to 0. So for steady state problem, whenever there is a convection, we'll be using this shell energy balance equation whenever there is a convection. So rate of combined energy flux in minus rate of combined energy flux out plus rate of work done on a system by external forces plus rate of energy production, that is equals to 0. So with this, we'll start our discussion on next problem. Actually, before going in that problem, we'll discuss viscous heating. So when there will be a rubbing of two layers of the liquid, so viscous, that there will be some energy lost will be there, and that loss of energy will appear as a heating, that is called as a viscous heating. So, and this you might be experiencing. So if you see whenever there is a ball bearing and ball bearing, so the most common example is actually your bicycle. So bicycle, your tire of the bicycle is connected to axle by using ball bearing actually to reduce the friction. And in that cavity there will be a oil is placed, some viscous fluid is placed, any viscous fluid, oil is placed. Now whenever you are riding a bicycle, there will be a continuous motion of this viscous fluid, and this viscous fluid is rubbing against layer by layer. Amongst the fluid itself, there is no solid to solid contact, but fluid itself is rubbing with one layer to another layer. And if you touch the axle of your bicycle after riding a few kilometers, you will feel that it get heated up. Because of that viscous heating is appearing actually, that whatever with the energy lost because of this viscous rubbing, it will appear as a heat, and that is called as a viscous heating. So we'll have discussion on viscous heating. Consider there is a two layer. So this is the stationary layer, and this is the top layer, which is the moving with the velocity v. This is stationary layer, and this is velocity moving with the velocity v. And generally, this gap will be very small. Whenever viscous fluid is used, generally it is avoid to the metal contact between the two surfaces. So, and this gap will not be very large. This gap will be very, very large. So velocity profile, and this is stationary plate, this is stationary surface, this is moving surface. So as this distance is very, very small, so we can assume a linear velocity profile. We can assume a linear velocity profile, and this linear velocity profile, now you should be able to give the profile, velocity profile equation directly. This you can do. You can do a shell balance, momentum transfer shell balance, or you can use equation of change and solving that, then you can get this velocity profile. But here this velocity is VB, and I am saying that there will be linear velocity profile, and this is horizontal direction. Gravitational force is zero actually. Gravitational force is negligible whenever this gap is very, very small. So viscous forces will be dominating over gravitational force. So this velocity profile will be VB x by V. So at x equals to 0, velocity is 0, and at x equals to B, this is at x equals to B. B is the distance between these two plates. Velocity is VB. So linear variation V x by B. So this will be the linear velocity Vx. So now you can see the rate at which work is done by a molecular motion. Okay. What will be a rate at which work is done by molecular work is done? So the rate at which work is done is the force acting on upper plate. Okay, force acting on upper plate times the velocity. This already we have discussed couple of slides before. That is what I was asking, whether you was clear. Force multiplied by velocity. Force multiplied by velocity in which it moves. Okay, this will be a force. Shear stress multiplied by area. Force multiplied by velocity will be the rate at which work is done. So rate at which work is done because of molecular transport. The rate at which work is done because of molecular transport will be this will be a force. Force multiplied by velocity. Force multiplied by velocity, and now this tau xz is related with a vz actually. So this will be a x momentum flux. This will be a z momentum flowing in x direction. So now rate of energy added per unit volume. So if I whatever be the this work, that will be if I want to interpret as the energy added per unit volume divided by volume. Divided by volume, what will be volume of total? This will be that will be a WL into B. This will be volume of that whole. You can say layer, volume of a layer. That so energy. So rate of energy added per unit volume, that will be this divided by volume, W into L into B. W into L into B, and substituting Vz as Vb x by V. So tau xz will be equals to minus mu dVz by dx. So dVz by dx will be a Vb by V. dVz by dx will be a Vb by V. Substituting both here actually, substituting both here, and rate of energy added per unit volume, rate of energy added, rearranging the equation. So first of all, this will be a rate at which work is done. That will be equals to force multiplied by velocity. And if I want a rate of energy added per unit volume, so this will be the volume of this film, and substituting, this is the velocity profile, and this shear stress is associated with velocity profile using Fourier law of conduction, Newton's law of viscosity. So Newton's law of viscosity, substituting dVz here and substituting this value here per unit volume, what I will get? So rearranging the equation. So rearranging the equation, what you will get? So this will be equals to mu Vb by B square. So what is this? This will be a rate of energy added per unit volume because of molecular transport, viscous heating. Because of this viscous heating, this will be a energy added, and this is called as a viscous heating. This is heat increase in a temperature because of the rubbing of one layer of liquid with another layer of liquid. So mu Vb, velocity, divided by distance square, that will appear as a, this is the energy appears as a heat, and hence it is called as a SV. So that is a heat added because of viscous dissipation. This is SP is a heat added because of viscous dissipation. This is clear? Roll number 95, Satyam. Is it clear to you?
Yes.
Okay. Can you just explain? The heat per unit because of viscosity. Yeah.
Sir, viscosity is so
Okay. So I'm not able to hear properly. Anyway, we'll continue with our problem with this brief discussion over combined energy flux. This is the problem actually. So this is exactly bearing problem. Consider a flow of incompressible Newtonian fluid between two coaxial cylinder of a bearing. This is cylinder of a bearing as shown in figure. So this is inner cylinder of the bearing. This is outer cylinder of the bearing. So this bearing is connected with, so this say inner axial is stationary and outer surface is moving, and this is common example in as I told in any wheels of any moving vehicles. So axial will be stationary, only your tires will be moving actually. Wheels are moving, but axials are stationary. So this will be connected to wheels and this will be connected to axle. So this will be inner cylinder is stationary and outer cylinder moves with the angular velocity omega. Okay. So surface temperature of inner and outer cylinder is maintained. So this surface temperature of inner cylinder is maintained at T0, forcefully maintained at T0 by removing the heat or adding the heat based on whatever be the temperature of the fluid, and surface temperature of the outer surface is maintained at temperature TB. Okay, surface temperature of outer surface is maintained at TB respectively. At steady state, T will be the function of R alone because the distance is very, very small, and this is you can say L is very, very large, so neglecting end effects, and this is symmetric around theta. So T is a function of R only. So it is given also, and you can also logically say that because it is not a function of L, the direction perpendicular to the screen is a L, length of the cylinder. Length of the cylinder is very, very large, so end effects are neglected, and in theta direction, so this will be a symmetric problem. If outer cylinder moves with the angular velocity omega and the inner cylinder is stationary, derive the expression for temperature profile of the fluid in a cylinder. The distance between two cylinders is very, very small as compared to radius of the cylinder. So the distance is very, very small. As the outer cylinder rotated, each cylinder shell of the fluid. So because fluid also start moving. So if you take a no slip condition, this is rotating with a velocity v omega, r omega. Okay, this is rotating with a velocity r omega, and this is a stationary 0. So because of this cylinder rotate, the fluid shells also move and rub against adjacent shell, because one layer of the fluid is moving with higher velocity, another layer of the fluid with moving with a lower velocity. They rub against each other, and this friction between adjacent layer of the fluid produces heat. The friction between this adjacent layer of the fluid produces the heat. This is what we have discussed just before. Viscous dissipation, heat appear. This is the mechanical energy is degraded into thermal energy. So which energy is given to this fluid? Fluid is given with a mechanical energy. This mechanical energy, outer cylinder is rotated with mechanical energy. So this mechanical energy is lost, and it is appeared as a thermal energy. The volume heat source resulting from this viscous dissipation can be designated by SV, appears automatically in shell balance when you use combined energy flux, because this is work, this is related with the work associated with the molecular transport. Whenever there is molecules are moving, and so because of this movement of molecules, work will be associated with that work flux, that will be appear as a SV, that is kind of a heat added to this system because of viscous dissipation. So we need to handle this problem. So first of all, first assumption, as it is given that this distance, okay, so say this distance is B, okay, this distance is B and this is radius. So generally this radius will be very larger than B, because you will not find a bearing such that one bearing inner diameter of the outer bearing is very large as compared to outer diameter of the inner bearing. I'm talking about this radius and this radius. These radius are very close, and the space is given between these two metal part just to avoid metal to metal contact. So main purpose of this space will be to avoid metal to metal contact, and to avoid metal to metal direct touch, a fluid is placed, viscous fluid is placed between these two this thing, so that it will move properly. So generally this distance B is very small. So instead of this round shape in theta direction, we can assume a curvature of the cylinder in theta direction. This is curvature of cylinder in theta direction can be neglected to solve the temperature profile for the moving fluid. So this can be neglected. This is, instead of taking a cylindrical coordinate system, we can neglect this curvature in theta direction, because this B is very smaller. Okay, B is very smaller than R, or R is very larger as compared to B. So curvature in the cylinder can be neglected to solve the temperature profile for moving fluid in the annular gap. So this, instead of assuming this, so this is the stationary phase I will move, and this will be a surface moving upper surface. So instead of curvature, I will assume this stationary phase. So, and because this B is very small, so I can assume a linear velocity fluid. Linear velocity, say this is say velocity is 0, so here velocity will be r omega, and there will be linear variation of temperature profile, and there will be some variation of temperature profile. Temperature changes from T naught to TB. So expected temperature profile, so this will be expected temperature profile. Here temperature will be T naught, here temperature will be TB, and some temperature profile will be there that depends upon all viscosity and everything of the fluid. And velocity profile, the curvature in velocity profile also can be neglected, because this distance is very small, curvature is neglected, and hence directly I can get. So as I told, to get this velocity profile, you can use a shell balance for momentum transfer. So but here this distance is very small, so I can neglect the curvature in this velocity profile and linear velocity profile. So here velocity is 0, here velocity is Vb, that will be equals to r into omega. So velocity profile Vz, so Vz will be, so at with given x direction, Vz will be Vb into x divided by b. This will be the velocity profile. Z velocity profile. Z means here this direction, theta direction. Z will be theta. Here Z will be theta. So, and where Vb equals to r into omega. So curvature is neglected, and secondly velocity profile, curvature in velocity profile is neglected. This is because of r is very larger than b. R is very greater than b. Hence both the curvatures are neglected. So this is the velocity profile. Directly you can write. So if you want to, if you don't want to assume this neglecting this curvature, so all the problem will be a cylindrical coordinate problem, so difficult to solve. So with small assumption, r is very larger than b, So I can assume this neglecting in this curvature and neglecting in the curvature of velocity profile, I can get a velocity profile, as well as this cylindrical coordinate problem can be solved by using a Cartesian coordinate system. Okay, so this so as I told, whenever there will be a movement of molecule or convection is there, so instead of using conduction, convection and work flow, so we'll be using this combined energy flux in. So rate of combined energy flux in minus rate of combined energy flux out, that will be equals to 0, because there is no heating, there is no chemical reaction, energy is not produced, or there is no heating, or external forces are not there. Just this will be combined energy flux, balance of combined energy flux. So what will be the differential shell? This will be because this velocity is varying only here in r direction, here it is x direction. This r direction is x. So there will be only a x differential thickness will be only in x direction. Differential thickness, it is not varying in z direction. Here theta, okay, here it will be theta, because problem is symmetric. It is not varying in y direction because end effects are neglected. Okay, so differential thickness will be only in x direction. This will be delta x because my properties are varying only in x direction. So now I can use what will be the volume of this differential shell. Say L is the length of the cylinder. So you can have this theta 2 pi r equals to width, that will be width into b. This distance is b. So this is my system. Okay, this is my system. That will be total volume. And this volume of this differential shell will be a L into W into delta X. So now, since the fluid, so energy balance over, since the fluid is moving, so use combined energy flux. Instead of using conduction, convection and work associated with molecular flux, we will be using combined energy flux. So this is what? A rate of energy coming in by combined energy flux minus rate of going out by combined energy flux, that will be equals to 0. This divided by volume of a differential shell. Divided by volume of a differential shell, volume of a differential shell will be a width length multiplied by delta x. So dividing it by volume of a differential shell, W into L into delta x, and letting delta x tends to 0, what I will get? D by dx of Ex equals to 0. This is combined energy flux in x direction. How the energy flowing in x direction? By combined mode of transport, convection, conduction plus work flux. This is clear to everybody, very easy. Anybody has any doubt? D by dx of this here x, in actual problem it is theta. That problem is transported considering neglecting curvature into a Cartesian coordinate system. So theta is transported to x. So d by dx of Ex, that will be equals to 0. Okay. Now this integrating this equation, Ex equals to C1. Now I don't have this any boundary condition related to combined energy flux. I have a boundary condition with respect to temperature. Now certainly I need to bring back the definition of combined energy flux. Now combined energy flux is a combination of convective energy flux plus this will be a work associated with the molecular flux for conductive energy flux. Now this Ex will be this is a convective energy flux in x direction. This will be a work flux in x direction, and this will be conductive flux in x direction. Now you know that Vx equals to 0. There is no velocity in x direction. Velocity is there only in z direction only. So this is equals to 0. Vx equals to 0. I have velocity only in z direction. Velocity is there in z direction, and substituting the definition of this work flux. This work flux. So now this is work flux, actually work flux plus conductive flux. This convective flux in x direction will be equals to 0. And this work flux, definition of work flux, x work flux. This is the x momentum flux because of x velocity. This is x momentum flux because of y velocity. This is z momentum flux because of z velocity. Now again using the definition of this total momentum flux, this will be a momentum flux because of viscous forces. This is because of pressure process multiplied by Vx. This will be a viscous forces only. Again, Vx equals to 0, Vy equals to 0. This Vx equals to 0, only Vz is non-zero. So ultimately pi into Vx, x will be equals to tau xz into Vz. Okay, this will be tau xz into Vz. So overall, this combined energy flux, okay, this will be equals to this substituting the Fourier law of heat conduction here. So Newton's law of viscosity here, substituting Newton's law of viscosity, and this is Fourier law of heat conduction for this conductive energy flux. So total energy flux Ex will be equals to minus k dt by dx minus mu dvz by dx. This will be combined energy flux. Now you can see that this is what? This is nothing but the work associated with a molecular transport. Because of molecular motion, whatever be the work is associated, this is work done on the system because of molecular transport. So this is combined energy, and this is the Fourier law of heat conduction, conductive heat flux. So this will be a combined energy flux. Now substituting this combined energy flux in my definition in Ex equals to C1. Now solving this Ex, substituting Ex, substituting Ex. So this will be minus k dt by dx minus mu dvz by dz plus equals to C1. Now you can solve this. Now for solving this, you need to solve. This is again multivariable single dimensional equation. This is one is temperature, one is velocity. This is one variable is temperature, one variable is velocity. So, and this temperature is varying in x direction, this velocity is varying in x direction. So to solve this, to get the velocity profile equation, we need to go back to a momentum flux. Okay, momentum flux, use shell balance equation or equation of change and get the velocity profile. But here, as we are assuming r is very, very larger as compared to b, so already we have this velocity profile. Already we have velocity profile, and using that velocity profile, I can estimate this term, substitute this term, then this will be a single variable differential equation. Okay, this will be single variable differential equation. What is the velocity profile? So already we have assumed velocity profile Vz equals to Vb x by b, and this is true when this gap is very small as compared to radius. This gap b is very small as compared to radius, then only this is true. Okay, if Vz is this, what will be dVz by dx? dVz by dx will be equals to Vb by b. So this dVz by dx will be a Vb by b. Substituting this Vz here, Vb into x by b, and this will be a Vb by b. So substituting this, so this differential will be eliminated. Differential of the variable velocity will be eliminated with this constant. And you can see this mu Vb by b square is nothing but can be interpreted as a heat appearing because of viscous dissipation. Heat appearing because of viscous dissipation. Now this problem can be solved if I have temperature boundary condition. Temperature boundary condition. Again, this differential equation is there. So I have two temperature boundary condition. Now this is mu into Vb by b square is the rate of viscous heat production per unit volume. So this is called as a heat appearing because of viscous dissipation. Now integrating this equation, what I will get? T will be equals to mu by k, rearranging and integrating this equation, x C1 and C2. So for this I need two boundary conditions. Whether these two boundary conditions are available? Yeah, roll number 96, Saurabh.
Yes.
What are these two boundary conditions? Can you write in chat box, Saurabh? Boundary conditions. So what are these two boundary conditions? So these are the two boundary conditions you can see, T0 and TB. So at x equals to 0, so at x equals to 0, this is my x direction. So at x equals to 0, so this is now converted to a Cartesian coordinate system. At x equals to 0, t is t0. At x equals to b, t is tb. So substituting this boundary condition and evaluating the constant and substituting, so this will be a temperature profile. TB not equals to T0. When TB is not equals to T0, then I will this temperature profile is this is actually the temperature profile with this boundary condition. And this is called as a Brickman number. Okay, this is Brickman number. So mu VB square K TB minus T. This is Brickman number, mu VB square. Brickman number is the dimensional, which is the measure of importance of viscous dissipation term. So this is kind of how much heat is generated because of viscous decimation and how much heat is transported because of conduction. This is the ratio of that two terms actually. VB square by B. Actually, this you can say VB square by. So this representing a heat generated because of viscous decimation and this thermal conductivity into temperature difference indicate the heat transported out, and that ratio of this two is a Brickman number, okay, which is the measure of viscous dissipation term. So this is viscous dissipation term, and this is the temperature profile. This is case 1 when TB not equals to T0. If both temperature are T0, if both the temperatures are T0, so here I can use this at x equals to 0 because that rearrangement was such that is not true for T equals to T0. So at x equals to 0, temperature is T0. At x equals to B, temperature is T0. So substituting and evaluating the constant, this will be, so this is kind of Brickman number actually. This is kind of Brickman number, not exactly Brickman number. This will be the temperature profile. This is second case. When both the temperature of the bearing, both the wall temperature is kept at temperature T0, some cooling or something is done. Or sometime what will happen, one wall temperature is maintained and another flux is maintained actually. Thermal, and this is insulated. Say this is insulated means thermal conduction will be 0 at x equals to B. Okay, this will be case number 3. Case number 3 is such that inner wall temperature is T0 and outer wall is maintained at flux equals to 0. Outer wall is flux equals to 0. Now, how to do this flux equals to 0 means here dt by dx will be equals to 0. Now that dt by dx I can calculate C1, and then at x equals to 0, t equals to t0, you can calculate this C1. So substituting that x equals to 0, t equals to 0, x equals to b, qx equals to 0, qx equals to 0 means dt by dx equals to 0. Substituting this and evaluating, so substituting this, and this will be the temperature profile with this boundary condition. Okay, so these are the three cases. All mathematics get the value of C1 and C2 for all the three cases. For all the three cases, all the three cases get both the constant and rearrange the equation. This will be a temperature profile when one surface temperature is T0, another surface temperature is TB, and this is both the surfaces maintained at temperature T0. And say this is the one surface temperature is given and another flux is given. Flux is given, that is equals to 0 in this case. Sometimes flux can be given. If flux is given with some value, so that can be substituted here. Here flux is given equals to 0, and if we rearrange this equation, this will be the temperature profile. On same line, based on conduction, only conduction and convection, there are few problems. Okay, this is take home assignment for you. If you want to solve, you solve, but these are the important problem, all important problem you should know, and exactly same fundamentals are used, nothing more than that, what we have discussed in a class. This will be a few more problem we are going to discuss in this heat transfer, but based on whatever topics we have covered. So this will be solved problem in DSL. Chapter number 10, 6 problem. Chapter number 7, chapter number 10, 7th problem actually. 10.7 and 10.6. This section you need to work as an assignment. Then unsolved problem in A section, 10 chapter, A section 1 to 4, and then 6 to 8, and then B section 2 to 6. Solve this problem. Okay, so we'll continue heat transfer only. Now we will touch some different aspects. So this is based on convection and conduction, whatever problem is there. So 4-5 problem we are discussing in a class, and these are the assignment problems. Okay, any